Last time we talked about integral operators, and now we're going to start discussing differential operators. So we have two types of differential operators. The gradient operator tells us the position dependence of a scalar field. And we also have curl and divergence operators that act on a vector field and tell us the position dependence of the vector field. Now, in all of these operators, we use the del operator to describe the curl, divergence, and gradient, and it is the one used for all fundamental differential operations. And the del operator, the gradient operator actually, is defined as using the subscript summation notation, ei hat, the partial derivative with respect to x sub I. Now, for the gradient, this operator acts on a scalar field to produce a vector field. And for example, the del operator acting on this scalar field phi, which is position dependent, x1, x2, and x3, this will be ei hat, the partial derivative of phi as a function of the coordinates x1, x2, and x3 with respect to xi. And notice that we have the I index repeated, so this is actually a summation. Now we can demonstrate that with the electric field. We know that electric field is given by minus the electric potential phi gradient. So electric field E is minus gradient of phi, and this would be minus ei hat del phi, partial derivative of phi, which is position dependent, x1, x2, x3, it's a scalar field, with respect to xi and addition over the I. So I can take values here, 1, 2, and 3 for Cartesian coordinates, for example. Divergence, on the other hand, the del operator acts on a vector field to produce a scalar using the dot product. So when I apply the del operator on a vector field with the dot product, with vector A, this will be ei hat, my del operator, partial derivative with respect to xi, dot product with my vector A, aj, ej hat. So ei hat dot ej hat is equal to 1 when I is equal to j. So this is the partial derivative of the ith component of vector A with respect to xi. And here I also have a summation. Okay, for example, the charge density is related to the electric field as rho is equal to epsilon 0, permittivity of free space, divergence of the electric field. On the other hand, the del operator can act on a vector field to produce a vector using the cross product. So del operator curl with vector A is going to be the ith component ei hat del xi, that's our del operator, cross product with vector A, aj, ej hat. This is going to give us del Aj del Xi Ek hat epsilon ijk. So first we look at the ith component of the first vector. Remember, in our cross product, so this is epsilon ijk. The ith component is del xi, and then we have the jth component of the vector aj, and this is in ek hat direction with the Levi-Civita symbol. I can give an example from Maxwell's equations. The electric field is related to the rate of change of magnetic field as curl of the electric field is equal to minus the rate of change of the magnetic field, del B, del T. This is one of Maxwell's equations. Okay, so we've talked about differential operators. The del operator, without anything else here, makes a gradient operator. If we apply it using the dot product, it is divergence. If we apply it using the cross product, it becomes curl. Now the del operator is ei hat del xi using subscript summation notation, and when it acts on a scalar field to produce a vector field, it's ei hat. We take the partial derivative of phi with respect to xi and we add over the I index, so I can take values 1, 2, 3 here. The example is electric field, which is minus gradient of the electric potential phi. If we take the dot product with the del operator and the vector, now we have a scalar at the end, and that's going to be the derivative, partial derivative of the vector A with respect to xi, the ith component, and this is summation over the ith component. For example, the charge density is permittivity of free space times the divergence of the electric field, and the curl produces a vector as well. So here, using our definition of the curl using subscript summation notation, we have del aj del xi ek hat epsilon ijk, that's curl A. So this produces a vector, and a good example is from Maxwell's equations. Curl of the electric field is minus the rate of change of the magnetic field. Next, we're going to talk about the physical picture that describes the divergence, curl, and the gradient operations.